Now we are starting the second part of chapter 11 of Levine's book, and that second part, 11.2, deals with the factorial design. That's two-way analysis of variance. Here we will have two factors to analyze: the supplier and the loom. In the previous part, we only looked at suppliers, and that was one factor. That's why we have two-way and y-way analysis of variance that corresponds to the number of factors we're analyzing. Let's just read what they write. In section 11.1, you learned about the completely randomized design used for situations concerning one factor. In this section, the discussion is extended to the two-factor factorial design. Let's highlight this. Two-factor factorial design, in which two factors are simultaneously evaluated. Each factor is evaluated at two or more levels. That's something important as well. For this to make sense, each of these factors have to be evaluated at two or more levels. Otherwise, their presence is unchanged. Is that correct? So the second factor that we have here is two brands of the loom. Otherwise, if we keep it at one level, we're going back to one-way ANOVA because the presence of this factor changes nothing. Okay, so each factor is evaluated at two or more levels. For example, in the using statistics scenario, Perfect Parachutes is interested in simultaneously evaluating 4 suppliers and 2 types of looms. While discussion here is limited to 2 factors, you can extend factorial designs to 3 or more factors. See references 4, 5, 6, and 8. Okay. Data from a 2-factor factorial design are analyzed using two-way ANOVA. 2 factors lead us to two-way ANOVA. Because of the complexity of the calculations involved, you should use software such as Microsoft Excel when conducting this analysis. However, for purposes of illustration and better conceptual understanding of two-way ANOVA, the decomposition of the total variation is presented next. The following definitions are needed to develop the two-way ANOVA procedure. R, here, the number of levels of factor A. C, the number of levels of factor B. We have 2 factors at least 2 levels each. N prime, number of values or replicates for each cell, combination of a particular level of factor A and a particular level of factor B. N, number of values in the entire experiment. So the difference between these two is we're going to enter our values in cells. And that'll have to do with the combination of a particular level of factor A and a particular level of factor B. That'll have to do with the interaction. And number of values in the entire experiment. That's the combined number of data points. We get R from here, C from there, and N prime. That's how many values we're going to have to look at. Okay, X sub I j k, the value of the kth observation for level I of factor A and level j of factor B. Okay, going back to grand mean once again, it's just the entire number of data points divided by their number. This is the sum of data points divided by their number. That will give us the grand mean, very similar to one-way ANOVA. The mean of the ith level here, the mean of the ith level of factor A, okay, another mean of the jth level of factor B. And here we go, mean of the cell ij, the combination of the ith level of factor A, let's highlight both of these, and the jth level of factor B. This text deals only with situations in which there are an equal number of replicates. That is, sample sizes and prime, for each combination of the levels of factor A with those of factor B. See references 1 and 9 for a discussion of two-factor factorial designs with unequal sample sizes. Okay. Rubric: Testing for factor and interaction effects. This is a very important term. We're going to be looking at interaction effects. There is an interaction between factors A and B if the effect of factor A is dependent on the level of factor B. In other words, you can have a strong parachute woven on one loom from the fibers from supplier 1, but a different loom supplied by a different vendor using these same fibers may not create such a strong parachute. That's how the two levels of second factor, which is the brand of the loom, these two levels affect the value of the first factor, which is the supplier of the fibers. Thus, when dividing the total variation into different sources of variation, you need to account for a possible interaction effect, as well as for factor A, factor B, and random error. That will be a separate term in the equation, little e, or epsilon. To accomplish this, the total variation, SST, not variance, it's variation, is subdivided into sum of squares due to factor A, SSA, sum of squares due to factor B, SSB, sum of squares due to the interaction effect of A and B, or SSAB, sum of squares of A and B, and sum of squares due to random error, SSE. This decomposition of the total variation, SST, sum of squares total, is displayed in figure 11.9. And by sum of squares, again, we mean actually squared differences between a value and the mean within each group. Over here we have it written mathematically. Factor A variation, factor B variation, interaction variation, and they all have their corresponding degrees of freedom that show us how much the values, in how many ways the values can vary. And random variation, that's error. This error has to do with the error of measurement, bad measuring instruments or different measuring instruments, or wrong protocol, some violations of protocol, measurement protocols. This is something that is usually called non-systemic. This error can hopefully be controlled. The sum of squares total, SST, represents the total variation among all the values around the grand mean. Equation 11.7 shows the computation for total variation. We take all data points, all possible, subtract the grand mean from them, which was calculated from these, and square the difference and then add up according to the ways they've been subdivided. We have R's for factor A, C's for factor B, and N primes for the interaction of those two factors, or as they put it, combination. The sum of squares due to factor A, SSA, represents the differences among the various levels of factor A and the grand mean. This is the first step in computing this, which actually brings us back here. We get our grand mean and all the values in factor A. After which we multiply this whole thing by C times N prime. Because factor A is present in a combination of A and B. The sum of squares due to factor B, once again, we don't only get A, then we'll get AB. That's why we have to have this little number here. Because we'll go back to these values when we start looking at combinations of A's and B's. The sum of squares due to factor B represents the differences among the various levels of factor B and the grand mean. Same story. This is the equation 11.9. Let's put little rectangles around them. That'll tell us that we have looked at these. Okay. And here comes the interaction variation. As I mentioned, they suddenly switched to the word combination. But we only have N prime, because for interaction values we don't need C or R. We already counted for those. Okay. The sum of squares due to interaction, SSAB, represents the interacting effect of specific combinations of factor A and factor B. Equation this one shows the computation for interaction variation. And this is the value of interaction mean, separate value of the mean for A, for factor A, then for factor B, plus the grand mean. That's how it goes here. And here's the sum of squares error, SSE. SSE represents the differences among the values within each cell. They keep talking about cells now. That'll be a group within each cell and the corresponding cell mean. All of a sudden the word cell is very actively used here. Equation 11.11 shows the computation for random errors. Well, here we are. They might as well call it the total error because they're taking into account every single value, every single data point we'll be dealing with. But they'll be only subtracting the mean of the interaction, xij. They're not showing how they calculate it. By the way, they're skipping all the means here, which is fine except for this one. This one has not been calculated. Let's see if they do it there later in the text. I don't think so. Because there are R levels of factor A, have R levels, factor A, R minus 1 degrees of freedom associated with SSA, sum of squares for factor A, due to A. Similarly, because there are C levels of factor B, C minus 1 degrees of freedom associated with SSB. Because there are n prime replicates in each of the R times C cells, there are R times C times n prime minus 1 degrees of freedom associated with SSE term, whatever is left for this, in whichever way to vary. Carrying this further, there are n minus 1 degrees of freedom associated with the sum of squares total, because you are comparing each value. This is each value, all values possible in this whole calculation. X sub I j k. You're comparing each value to the grand mean based on all n values, and n equals R times C times n. Okay, where is it? Here. I'm going to put a little rectangle around it so we can remember it well. Okay. Therefore, because the degrees of freedom for each of these sources of variation must add up to the degrees of freedom for total variation, SST, you calculate the degrees of freedom for the interaction component, SSAB, by subtracting. The degrees of freedom for interaction are R minus 1 times C minus 1. Makes sense. If you divide each of the sum of squares by its associated degrees of freedom, you have the four variances or mean square terms. The keyword is mean. The variance is the mean square. This is the square, and after being divided by R minus 1. After being divided by R minus 1, it makes this the mean square. That's how the average is calculated from it. Same goes for factor B. This is variation due to factor B. So for this square, sum of squares to become a mean, sum of squares we need to divided by C minus 1. Variance, 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 variance. Now we have four components for the equation. There are three distinct tests to perform in a two-way ANOVA. There are three distinct tests to perform in three-way ANOVA. Okay, in one-way ANOVA, we needed the Levin test, which incorporated ANOVA, but Levin test was used for variances and was based on median. We ran the ANOVA itself on means, that's the second test, and there was a post hoc test for different differences. There was the Tukey-Kramer. The Tukey-Kramer procedure, which was one of the many comparison procedures. And by the way, the Levin test, the very first one that should have been conducted, that was last, they showed. The Levin test was called the modified Levin test. what they showed was one of the versions of the Levin test. Okay, there are three distinct tests to perform in a two-way ANOVA. Here's the first one. To test the hypothesis of no difference due to factor A. Okay? The means of whatever we're measuring, such as tensile strength, the means don't differ. This is due to factor A, against the alternative that not all means are equal. Not all means due to factor A differ. And here comes the F statistic for the effect of factor A. MSA divided by error, which points us to the within group variations. So it's forcing us to stay there within the first factor. The influence is detected due to first factor. You reject the null hypothesis if the alpha level of significance, or at the alpha level of significance, if your F statistic, which is the ratio, is greater than the cutoff statistic. That's correct. So when this is greater than this, it lands this in the rejection zone, where F sub u is the upper tail critical value from an F distribution with R minus 1 and RC times n prime minus 1 degrees of freedom. Second step, to test the hypothesis of no difference due to factor B. Exactly the same. Null means are all equal. Factor B is not working. The alternative is that it is working because it causes the mu's to become different, not equal. This is the F statistic, which is the same formula. Mean squares due to factor B divided by mean squares due to error. You reject the null hypothesis at the alpha level of significance. If this ratio is greater, the F ratio is greater than the cutoff, the critical value, where F sub u, again, is the upper tail critical value got to cut this out, man. Critical value from an F distribution with C minus 1 and R times C same degrees of freedom as for factor A. Well, not exact same. For the denominator, same degrees of freedom for the denominator. Different for the numerator in the table. Here's the third step, to test the hypothesis of no interaction of factors A and B. Verbally stated null hypothesis. The interaction of A and B is equal to 0. You can just multiplication, put the multiplication sign. And the alternative is the interaction of A and B is not equal to 0. The calculation of F statistic is again the same. Mean squares due to interaction divided by the mean squares of the error. You reject the null hypothesis at the alpha level of significance if the F ratio that you calculate from here is greater, that is lands in the rejection region, is greater than the critical value F sub u, where F sub u is the upper tail critical value from an F distribution, upper tail critical value from an F distribution with R minus 1 times C minus 1 and This is for the numerator. And r times c times n prime minus 1 degrees of freedom is for the denominator. Okay. And here's the two-way ANOVA table. Basically an expanded one-way ANOVA table. To examine a two-way ANOVA, return to the using statistics scenario on page 422. As production manager at Perfect Parachutes, you have decided not only to evaluate the different suppliers, but also to determine whether parachutes woven on the Jetta looms are as strong as those woven on the Turk looms. In addition, you need to determine whether any differences among the four suppliers in the strength of the parachutes are dependent on the type of loom being used. Thus, you have decided to perform an experiment in which 5 different parachutes from each supplier are manufactured on each of the 2 different looms. These results are given in table 11.7 and stored in the parachute 2 file. Look, we have 1, 2, 3, 4, 5 times 4 times 2. We have 40 data points. Now we're going to have to start looking at the data file, and we'll do it in the next video.